in today's video, we are going to be learning about a family of aromatic compounds called phenols. So what I mean by a phenol is where you have your benzene ring and you have an OH group directly attached to that benzene ring. Okay, so that OH group is called a hydroxyl group, but this compound here is your simplest type of phenol, and this compound here is simply just called phenol. Okay, so if we look at naming other types of phenols, where we have possibly other substituents attached to it, so this one over here. So again, we need to use the term parent and substituent. In this case, the phenol group, so this part here is what we class as the parent, and this NO2 group, this nitro group, is our substituent. So the parent name goes at the end, so this is ending in phenol, and always when the phenol is the parent compound, the OH is attached to carbon number 1, and therefore this compound here is called 3-nitrophenol. So to do another example, like so. So again, we have chloro substituents over here, and our parent compound is the phenol part. So the name's going to end in phenol. We've got 3 chlorines, so it's going to be trichlorophenol, like that. And again, the hydroxyl group is on carbon number 1. So if we just put all the numbers in, this compound here is therefore called 2,4,6-trichlorophenol. Now, phenol is always the parent, except when it comes to the exceptions to the rule. So, for example, when we had benzoic acid, that's an exception. So benzoic acid would always be the parent regardless of what else is attached to the compound. So in this case over here, the benzoic acid, this part here, is the parent compound. So that means this is going to end in benzoic acid. And now the phenol, the hydroxyl group, is actually the substituent. So where the carboxylic acid is coming off, that's carbon number 1. So therefore, I'm going to go anti-clockwise this time in terms of numbering. The OH group is found on carbon number 3, and as a substituent, the hydroxyl group is called hydroxy. So this compound here is called 3-hydroxy benzoic acid. So as a substituent, the OH group is called hydroxy. Just be warned, if that OH group is not directly bonded to the benzene ring, so for example like this, this compound here is not a phenol. This is just an alcohol with a benzene ring coming off. Okay, so if we want to name this one, it's just the same rules as before. You've got a benzene ring, but you've got a functional group coming off of it. So this functional group here is the parent. So this compound here is ethanol. So this is going to end in ethanol. The OH group is coming off carbon number 1 because that's the parent, and therefore the benzene ring is a substituent, is phenyl, and therefore this is called 2-phenyl ethanol, like that. Okay. Right, if we now move on to the reactions of our phenol group, the first thing we need to know is that phenol can act as a very, very weak acid. And by a weak acid, I mean, so pH is usually around 5, obviously depending on concentration and which phenol you have, but it's quite a weak acid, as you can see by its pH. So if you want to show our phenol acting as a weak acid, it is this hydrogen here, this proton here, that is our acidic proton. So if we have our phenol in solution, it will slightly dissociate to form this ion over here and also release a proton. Okay, so this compound here is our phenol, and the ion that it forms is called a phenoxide ion. Like that, and that's obviously our proton. So that's us showing phenols acting as a very weak acid. And if we want to show acid-base reaction, we can show our phenol acting as an acid by taking part in this acid-base reaction. So the base I'm going to choose is just sodium hydroxide. So we've got an acid plus base. We know we need to make a salt plus water. So in this case, the salt that forms is that. And as you can see, we also produce a water molecule like that. Okay, now this salt over here, the name for this one is sodium phenoxide. So that's our phenol taking part in an acid-base reaction. If we want to compare the reactivity of our phenol, we can compare, because obviously we're calling it a weak acid, we can also compare it with another weak acid that we cover, and there are carboxylic acids. So we can compare the reactivity of phenol with a carboxylic acid. Now, given a phenol has an OH group, it might be worth looking at the reactivity of a phenol in comparison to an alcohol. So I'm just going to look at 3 types of functional groups. I'm going to compare alcohols to phenols and compare those to carboxylic acids. I'm just writing Q acid just to shorten that down. Okay, so by alcohol, can be talking about any alcohol like ethanol, methanol, anything with the OH group on it, as long as it's not directly bonded to a benzene ring. A phenol is where we have the OH group directly bonded to the benzene ring. Carboxylic acid is any of our organic acids like methanoic acid, propanoic acid, and so on. Okay, so we're going to compare the reactivity of all of those acting as acids. So, as we know, all acids take part in acid-base reactions, so we can look at the reactivity with different types of bases. So we can look at the reaction of these with strong bases. And so by strong base, the example that I used earlier was sodium hydroxide. So any hydroxide we can use for this, like it could be sodium hydroxide, potassium hydroxide, and so on. And we can compare it with weak bases. So weak bases are, for example, our carbonates, so our metal carbonates. So I'm just going to go for sodium carbonate, but it could be lithium carbonate, potassium carbonate, and so on. Okay. So when it comes to the acidity of an alcohol, we should know that alcohols are not acidic at all. In fact, their pH is probably going to be around 7. Okay. So when it comes to an alcohol taking part as an acid in an acid-base reaction, they don't take part in those sorts of reactions. They don't react with strong bases, and they don't react with weak bases either. They're not acidic at all to take part in acid-base reactions. So if you react or try to react an alcohol with a strong base or a weak base, you should have no reaction whatsoever. Okay. Now, in terms of acidity, so we said alcohols weren't acidic at all. Phenols we know are very weakly acidic. So when it comes to their reactions, because they're so weak in terms of their acidity, they're only going to react with strong bases. Okay, so as we said in the reaction that I did earlier, it was phenol reacting with a strong base. It was sodium hydroxide, and therefore the reaction occurred. But if we tried to react a phenol with a weak base, like sodium carbonate, you wouldn't see a reaction at all. There would be no reaction. Okay, so the key part here is that phenols only react with strong bases like hydroxides. They don't react with weak bases like carbonates. And carboxylic acids, so in terms of pH, I would say they'd be around about 3. obviously depending on concentration and which acid you're looking at, but they're still classed as weak acids, but they are slightly stronger than phenols. So in terms of their acidity, in terms of their reactions, they take part in reactions with strong bases, and they take part in reactions with weak bases. So you should have done reactions where you have, for example, ethanoic acid with sodium hydroxide, and that is a neutralization reaction. If you add sodium carbonate to, for example, ethanoic acid, you will see an observation, you'll see a reaction, you'll see carbon dioxide bubbling from that reaction. Okay, so in terms of reactivity, you need to be aware of which out of alcohols, phenols, and carboxylic acids react with which ones of the bases, the strong bases or the strong acids. The weak bases. So yeah, in terms of reactivity, that's what you need to cover. So phenols, the take message from here is that phenols react with strong bases, but they do not react with weak bases. You should not observe a reaction when you add a carbonate to a phenol. Right, so that's reaction type number 1, where phenols are reacting they're acting as weak acids with strong bases. Let's now have a look at the aromatic part of it, the benzene ring part of it, taking part in reactions. Okay, so when it comes to benzene, we've seen the mechanism that it undergoes. It is electrophilic substitution. And we'll find that phenols also undergo electrophilic substitution as well. Okay, but in terms of reactivity, it actually reacts slightly differently to how just a benzene ring would. Okay, so let's look at reaction number 1, and this is the bromination reaction. So we are going to be reacting with bromine. So we have our phenol. And if we react that with bromine, when we're doing the reaction of benzene with bromine, we had to have a halogen carrier to act as a catalyst. Whereas in this reaction, we don't actually need a halogen carrier. Okay, and that is because phenol is more reactive than benzene. We'll learn in another video why that is the case. But the substitution will occur at room temperature and pressure without any catalyst or any halogen carrier present. In this case, the substitution won't just occur once, it's actually going to happen 3 times, like that. Okay, and given a substitution reaction, obviously we've got to produce another product as well. The other product is going to be HBr. In order to balance this, you need to have 3 bromine molecules, because obviously the substitution occurs 3 times, and therefore you're also going to release 3 hydrogen bromide molecules as well. So that's the overall reaction. For the bromination reaction, doesn't require a catalyst or a halogen carrier for this. You do need to know the name of this product, so let's have a think about what the name of this product would be. The phenol is the parent compound, so it's going to end in phenol. You've got 3 bromos, and they're coming off at 2, 4, and 6. So therefore this compound here is called 2, 4, 6 tribromophenol. Okay. And in terms of what you would observe in this reaction, you're actually going to make 2 observations. So if we jot down the observations over here, you're going to see 2 observations. The first thing is that 2,4,6-dibromophenol is a solid, so you're going to see a precipitate or precipitation. So observation number 1 is that you'll actually see a white precipitate. So it's a white precipitate that forms a white solid that forms. So that's observation number 1. Observation number 2, so you're reacting with bromine. Bromine is an orange-brown liquid at the end. You shouldn't have any bromine left, and therefore the orange-brown colour should disappear. So the second observation is that it decolorizes bromine water. Okay, so observation number 1, observation number 2. And you need to know, if they ask for the observation in an exam, you have to jot down both those observations. Right, reaction number 2, and again, this is going to undergo electrophilic substitution. And this is the nitration of a phenol. So as we did with our benzene ring, we've got to react this with nitric acid. Now, in the reaction of benzene, for it to undergo nitration, we had to use concentrated nitric acid, and as a catalyst, we had to use concentrated sulfuric acid. Now, for the nitration of phenol, you actually need much milder conditions. So you don't actually need concentrated nitric acid. Dilute nitric acid will work just fine. Okay, so you have your phenol, you have dilute nitric acid, and this time you don't need a catalyst. You don't need the concentrated sulfuric acid, and you don't need to heat it up to 50 degrees Celsius. Okay, so you just need to do this at room temperature and pressure without the presence of a catalyst. And this should cause our substitution to occur. Now, the substitution will usually occur in position number 2, so it's usually going to be on the second carbon, or it can also be on the 4th carbon. We've got no way of controlling which carbon, I don't know if you can see that, but we've got no way of controlling which carbon it reacts with. Okay, so it can react with carbon number 2 or carbon number 4. So you usually get a mixture of these two products. You usually get a mixture of 2 nitrophenol and 4 nitrophenol, and just also don't forget you also produce a water molecule in each of those as well. Okay, so they're the reactions that our phenol will undergo, and as you can see, there are much milder conditions, and we're going to look at why that's the case in our next video.